Okay, folks, I sure hope that yesterday, Tuesday, went pretty well um, in class. And I have one more little thing I want to talk about in order to finish up our discussion of thermodynamics. So we've talked about heat engines and we've talked about the laws of thermodynamics. There are four of them. The first one is kind of silly. The first one is the temperature is equal. The second one is about how energy is conserved, and that includes work done. And uh, the second one says that heat only naturally flows from high temperature to low temperature. That will come up today because entropy explains that. And the last one says that nothing can happen unless the total entropy of the universe is increased. It actually says the total entropy of the system is increased, but the biggest system of all is the entire universe. But you can look at smaller sections of the universe, which we call the system. I bought some new pens. These are full-on Sharpies, which I don't normally use, so I really hope that I'm not accidentally marking through the papers onto the table. Anyway, the first thing I want to tell you is that the definition of entropy. Entropy gets the letter S for some reason. I don't know what it is. And people say that entropy is a measure of the disorder of something. And I showed you a video to kick things off, and that wasn't quite the answer that the Veritasium people gave. They said that it's more like it's the spread out nature. How spread out? Let's do this. How spread out is the energy. And the more spread out the energy is, the more disordered the system is, the more likely it is to be that way. In other words, having all the energy concentrated in one place is very unlikely to happen, and spread out is more likely to happen. There are more different ways for it to be spread out and very few ways for it to be concentrated. When we do calculations, we always calculate the change in the entropy. After all, the total entropy change has to increase. And the change in the entropy is defined as the amount of heat that flows divided by the temperature at which it flows. And this number up here can be positive or negative. If heat is leaving a system, we would get negative, and if heat is entering a system, we would get positive. And this temperature is in Kelvin. We can't have zero in this denominator or that would blow up. And since 0 Kelvin is absolute zero, which you can't get to, we're safe using Kelvin as the temperature scale here. So let me show you some examples. Let's do something really simple. Let's just talk about the sun. Let's have some energy leaving the sun. 100 joules of energy leaves the sun. And arrives at Earth. Does this violate the third law of thermodynamics? Is the total entropy of the universe or the Earth-Sun system, is it increased? Boy, I'm really unhappy with this focus here. I may have to change software at some point here, but we'll keep plugging along. So we have here a picture where we have the sun, and I'm not very good at drawing the sun. I seem to remember some sort of emoji that had the sun wearing sunglasses, which is hilarious. And so we're going to have 100 joules of energy. Lovely, they're mowing. Going from the sun to the Earth. Now we need the Earth to have some continents on it because we don't want the Earth to be incontinent. So the change in entropy of the sun is going to be the loss of 100 joules, and that happens at the temperature of the sun. Now, the temperature of the photosphere, the part of the sun that's actually giving us the light, and I'm going to assume that this is a packet of radiation in the form of light, that is 5,772 kelvins. The core of the sun is 15 million Kelvin, but it's significantly cooler in the zone of the sun that actually makes the light that makes it to the Earth. And so we can get out our calculator and we can figure out that this number is going to be negative 0.017. And the units for entropy are joules per Kelvin. Just kidding. Now, for the Earth, the change in entropy of the Earth is going to be addition of 100 joules, and that's going to happen at the temperature of the Earth. And I don't know if we want to get fancy about the temperature of the upper atmosphere, but how about room temperature, which is about 20 degrees Celsius, which would make it 293 Kelvin. And we do that calculation, and we find that that's a positive 0.341 joules per Kelvin. So the total change in entropy is going to be, 0.324 joules per Kelvin. We subtracted, or we added this negative 0.17 to this 341. This is a positive number. Therefore, the third law of thermodynamics is satisfied, and this can happen. And we know it can happen because we do it all the time. The light from the sun comes and heats the earth constantly. Okay, let's apply this to another system here. Okay, so it's only letting spots through, so I think the one piece of paper is good protection for my table. What about your car? Let's talk about your car. Now, car has as its hot reservoir burning gasoline. And I don't really know the temperature of burning gasoline, so we're just going to call it burning fuel, and I'm going to make up a number, and I'm going to say that burning fuel in your car is 1,000 Kelvin. And the cold reservoir in your car is the atmosphere surrounding your car. Now, I'm going to grant that the exhaust of your car is warmer than room temperature, so I'm going to call that 300 Kelvin. It's not much different than what we had before, but it also is a nice round number. So if we were to draw a conceptual diagram of our car heat engine, we would draw this sucker right here. Hot reservoir at 1,000 Kelvin, cold reservoir at 300 Kelvin. We would do this, and we would steal some away as heat. I'm sorry, steal some away as work. I misspoke. So let us assume that we take 100 joules of energy out of the hot reservoir and we put 90 of it into the cold reservoir. How much work would have been done? And by the first law of thermodynamics, that would be 10 joules of work would have been done. So now we do the analysis of the entropy. The entropy of the hot reservoir is going to be a loss of 100 joules happening at 1,000 Kelvin for a grand total of minus 0.1 joules per Kelvin. The change in entropy of the cold reservoir is going to be a gain of 100 joules, and that's happening at 300 Kelvin. And so that turns out to be positive 0.3 joules per Kelvin. And when we sum these things up, you can see that overall we are getting an increase of 0.2 joules per Kelvin. So this is a perfectly legal thing to do. By the way, that first example with the sun and receiving energy from the the Earth receiving energy from the sun, that shows you why it is that heat naturally flows from high temperature to low temperature, because high temperature has a larger number in the denominator, so the negative that you'll get for the heat leaving is going to be smaller in magnitude than the positive you're going to get for the heat entering something else that's colder. So that's why entropy was latched onto as a tremendous thing to be talking about. You know, I used to do this thing where I would tilt this a little bit. Maybe I should do that. That makes it easier for me to write. But once again, we've got issues. So Sadie Carnot, who was talked about in the Veritasium thing, he wanted to know, well, what if I made an engine that was even more effective, even more efficient? He said, what is the most efficient engine I can make? And so we can work that out. We could say, well, how much could we take out here and still wind up with a thing, a good, what am I trying to say? We want a total a total change in entropy of 0. We want the change in entropy of the hot reservoir to be equal in magnitude to the change in entropy of the cold reservoir. Now, the change in magnitude of the hot reservoir is our 100 joules, and taken out at 1000 Kelvin. Cold reservoir, how much could we put in? How little could we put in? So I want to put an X there. We're going to try to figure out how little we can put in so that this turns out to be 1, and that happens at 300 Kelvin. And so when you cross multiply, you'll find out that the X, which is the heat going into the cold reservoir, can be as low as 30 joules. We took 100 out of the hot reservoir. We could put it as little as 30 into the cold reservoir, meaning that the work that we could get out could be as much as 70 joules. That's pretty impressive. So he figured out that the efficiency of any heat engine is 1 minus Q cold over Q hot. Then you multiply this whole thing times 100 if you're in America, because we like our efficiencies in percentages. And the maximum you can get is 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir times 100 if you're in America. So this is the maximum efficiency you can get. And for our two examples on this internal combustion engine, the maximum efficiency you could possibly make an internal combustion engine is 70 joules. Now, I may have let slip in class that the efficiency of a modern internal combustion engine is below 20%. So there is a theoretical maximum for those two temperatures of 70 joules. It's just that the current four-stroke engine has no way of getting even close to that. There are so many sources of friction, so much internal housekeeping, so many things that are taking additional energy away that there's no way we can touch this amount. This would be what would it be? It'd be 70% efficient because you're getting 70 joules out for 100 that you spent. So this is the Carnot efficiency. This is the maximum efficiency you can get. And to do that, he invented this cycle called the Carnot cycle, which is a theoretical cycle. Anything that you actually build will be worse than that. Okay, just wanted to share with you some things about entropy and what it is and how to do calculations involving entropy. And that is the last thing I will say about thermodynamics. There'll be a little question quiz thing on thermodynamics, or perhaps I'll write a GIM kit. I'm not sure. But that will be what you're doing today, Wednesday. Watch this video and do either a Google quiz or a GIM kit, depending on what I come up with later this afternoon. Hey, thanks for putting up with this. I will tell you that even my car was in worse shape than I thought. As I was trying to drive home, I got about 20 miles away from my house out here, and the thing started not going very fast. And it turns out that there's a 4-speed transmission, and third and fourth gear were not functioning, but the car kept trying to shift into them. So I was kind of limited to second gear, and I'm trying to drive home on a freeway where the speed limit is 70. So and every so often it's jumping into a gear that is effectively neutral. So I was never going to make it home yesterday, Monday, and unfortunately it's going to take them 4 days to fix my transmission. So I will see you guys next week, unless this turns out to really, really not be working for you, in which case send me an email, and then I'll maybe I'll take the Greyhound bus back home and teach a couple days. Anyway, good talking to you, and good luck with the worksheet.